right, so we have talked about using the R value, the correlation coefficient, to tell us how linear data happens to be, how strong of a linear relationship we have. We talked about R squared, the coefficient of determination, how much of the response or dependent variable can be explained by the explanatory or independent variable. And so now what we're going to do is we're going to take a look at the actual line that best fits that data. Okay, that line has a number a number of names actually, but the one that we're going to use the most often in here is the least squares regression line. Okay, you will also see it called at times the line of best fit. It's much less technical name, and the one that probably makes the most common sense to people. Okay, so those are the same thing. The line itself is written in this form, so it is y hat. Now remember, anytime we see that hat, that means we're basing it on a sample. Okay, so this is saying this line is coming from a sample, in this case, our sample of data about Old Faithful. Okay, so y hat is equal to, and this comes right off that linear regression on your calculator, ax plus b. Okay, so y hat is going to be a predicted value. So we're saying, based on the data we have, this is what we think is going to happen. Okay. The slope is a. You're probably used to hearing mx plus b in your algebra classes. This is the same exact thing. It's just the letter a. Okay, there's no difference. A variable is just standing in for something. And then your y-intercept is the point 0b. And that is the same y-intercept that you're used to seeing. Okay, so once we have the slope, again, it's not just about getting the equation, it's what does this equation mean and what are we going to do with it, all right? So the general interpretation of the slope is as follows, okay? This is how much y changes when x, oops, sorry, like my screen is wigging out here, when x increases by 1 unit, okay? And whatever that unit is dependent upon your data, okay? So for us, our data is about how many minutes long something is, so a unit would be a minute, okay? It could be the price increases by a single dollar. There's all kinds of things it could be, okay? So put the unit part in context. The interpretation of the y-intercept is the value of y when x is equal to 0. Now, there are times it makes no sense whatsoever to let your x variable be 0, okay? If we were, for example, comparing height and weight, and we were trying to predict somebody's height based on their weight, okay? So x is the weight and y is the height. It would be inappropriate to say someone weighs 0 pounds, because if you weigh 0 pounds, you're not a person at all. You weigh nothing and you have no height. So that's a situation where it wouldn't make any sense, okay? And then you just state it doesn't make sense to do that. All right, so let's go back to our good Old Faithful data, our good Old Faithful. Sorry, didn't mean to duplicate that so many times. All right, so from the least squares regression that you ran already, so linear regression, LINREG, AX plus B, you have an equation that pops up. It'll say like y equals AX plus B on your calculator, and it gives you a value of A, and it gives you a value of B. Okay, so we're going to use those values of A and B to write our equation. Let's go ahead and round to 2 decimal places. So y hat, our predicted line of best fit, okay, based on data, should be 11.14x plus 32.50. Okay, that's our equation. Now, let's do the things we just talked about up in the box at the top. Interpret the slope. Okay, so remember, for every 1 unit increase in X. Okay, so what is our X about? It's about how long an eruption lasts. So for every 1 minute increase in the duration of an eruption. Okay, so don't just say for every 1 minute increase in X. Tell me what X is. I don't know what X is. Okay, so for every 1 minute increase in the duration of an eruption, then the slope, so 11.41 minutes, and it's positive, right? So that means there is an increase, that's the positive part, of 11.14 minutes in what? Well, that's the time between eruptions. Okay, so for every additional minute Old Faithful is erupting, it's going to increase. Again, this is an estimate, but it's going to increase by about 11.41 minutes between the next eruption. Does it make sense to interpret the y-intercept of the regression line? So does it make sense for X, the duration of an eruption, to be 0 minutes? Well, no, because if it didn't erupt, there's no, I mean, if the eruption is 0 minutes, it never erupted. Okay, so it would not make any sense. So no, an eruption lasting 0 minutes, so that's when X is 0, does not make sense. So we're not going to interpret the y-intercept. Okay. Now, what else can we do with this line? Well, we can make some predictions. So if we watch an eruption that lasts 2.9 minutes, so again, we're talking about duration. Duration is our variable X. What would the line predict is the interval until the next eruption. So the interval until the next eruption is our y hat. What is our predicted variable or our predicted value? So knowing that X is 2.9 minutes, we would have 11.14 times X, 2.9 minutes, plus 32.5, just taking our equation from back in H. And we would find that it is a predicted duration between eruption, or not duration, interval between eruptions of 64.8 minutes. Okay, that doesn't mean that's exactly what's going to happen, but again, it's our best prediction. All right, one last thing here about this same example, and then we've got everything there is to know about linear regression all in one example. The residual is the error or the margin of error for your predicted value. Okay, so the residual is the y value, which is the observed value, the one that came from the data, minus y hat, the predicted value. Okay, so let's find the residual for an eruption that lasts 4.9 minutes. Okay, so what we need to do is go back and get the observed value. Okay, that goes all the way back to page 1 from the table. Okay, if you go 10 data values down, you will see when X is 4.9, Y was, I don't need to write that twice, Y was 76 minutes. Okay, so that's the observed actual what really happened. Okay, if we do our predicted value and we use our equation for y hat, okay, we would get y hat is 11.14 times those 4.9 minutes plus 32.5 is 87.1 minutes. Okay, the residual is the actual value, the observed value, 76 minutes, minus the predicted value, 87.1 minutes, or a difference of negative 11.1 minutes. Okay, what does that mean? Okay, what does that tell us and what does that mean? So the interpretation would mean the actual time between eruptions was 11.1 minutes less, hence the negative number there, okay, than what was predicted. Okay, so the actual time in between eruptions was 11.1 minutes less. Don't say negative 11.1 minutes. I don't know what that means. I don't know what negative time means, okay? That says it's 11.1 minutes less than what was predicted. If it's a positive residual, then that means it would be that much more than what was predicted. All right, so in the next example, we're basically going to walk through all of those steps again, but for a new set of data. So before you even go on to the next video, one of the things you might want to do is go ahead and take the time to clear out Old Faithful and put in this next data set so that you're ready to go.